Hello, science fans! Welcome to an incredible journey. We are about to dive into the world of quantum computing. Now that might sound complicated. It might sound like something from a science fiction movie, but I promise you, it's real. It's happening now, and you can understand it. Over the next 3 weeks, we'll explore this amazing field together. We will break it down into small, digestible pieces. Think of it as a 21-day challenge to unlock a new way of thinking about computers' information. Reality itself. This isn't just for physicists in a lab, it's for curious minds like yours. Welcome to Week 1. Our mission this week is to build a solid foundation. We'll start with the most fundamental building block, the qubit. A qubit is different. It can be a 0, it can be a 1, or a combination of both at the same time. This mind-bending property is called superposition. Think of it like a spinning coin. While the coin is spinning in the air, it's not heads, and it's not tails. It's in a state of both possibilities. Only when it lands and you look at it, does it become one or the other. A qubit is like that spinning coin. Superposition is the first superpower of a qubit. It allows quantum computers to hold and process a vast amount of information. If you have 2 classical bits, you can represent one of 4 possible combinations, 0001, 1011 at any given time. But with 2 qubits, thanks to superposition, you can represent all 4 of those combinations simultaneously. As you add more qubits, the power grows exponentially. With just a few hundred qubits, you could represent more combinations than there are atoms in the known universe. Now, how do we control these qubits? We use something called quantum gates. In a classical computer, logic gates like AND, OR, not manipulate the zeros and ones. They manipulate the zeros and ones. Quantum gates do something similar, but for qubits. They are like precise nudges that rotate the qubit state. Imagine our spinning coin again. A quantum gate could be a tiny puff of air that changes the angle of its spin. One of the most basic gates is the Hadamard gate, or H gate. This gate is what puts a qubit into a perfect superposition state, an equal mix of 0 and 1. It's like a perfect coin flip that starts the quantum magic. Finally, we need to get a result from our qubit. This is called quantum measurement. Remember, our qubit is in a superposition of 0 and 1, like our spinning coin. When we measure it, we are forcing it to choose a state. It will collapse into either a definite 0 or a definite 1. The probability of which one it chooses depends on its superposition state before the measurement. If it was in a perfect 50-50 mix, you have an equal chance of getting 0 or 1. This act of measurement is fundamental. It's how we get the final answer out of a quantum computation. This week is all about understanding these 3 core ideas: superposition, gates, measurement. We've reached the end of our first week. Welcome to Week 2. If you thought superposition was strange, get ready for something even more mind-boggling: quantum entanglement. Albert Einstein famously called it spooky action at a distance. Entanglement is a special connection that can exist between 2 or more qubits. No matter how far apart you separate them, across a room, across a city, or even across the galaxy, they remain connected. If you measure one of the entangled qubits and find it's a 0, you will instantly know that the other one is a 1 and vice versa. Let's use an analogy. Imagine you have a pair of magic gloves. You put one in a box and the other in a second box. You don't know which is the left glove and which is the right. The moment your friend opens their box and sees they have the left glove, you instantly know that you have the right glove. Before they opened the box, your glove was in a state of being both left and right. The act of measuring one instantly determined the state of the other. That's entanglement. It's a powerful resource for quantum computing. This spooky connection allows for incredibly complex correlations that are impossible in the classical world. It's a key ingredient in many powerful quantum algorithms and in technologies like quantum teleportation. Teleports information, not people. Building a quantum circuit often involves creating these entangled states. We use specific quantum gates like the controlled NOT or C-NOT gate to create this link. The C-NOT gate involves 2 qubits, a control qubit and a target qubit. If the control qubit is a 1, it flips the target qubit. If the control is a 0, it does nothing. This conditional logic is how we weave qubits' fates together. With superposition and entanglement in our toolkit, we can now start looking at quantum algorithms. These are the special recipes that quantum computers follow to solve problems. One of the most famous is Grover's algorithm. Think of it as a quantum search engine. Imagine you're looking for one specific name in a giant unsorted phone book with 1 million entries. A classical computer would have to check each entry one by one. On average, you'd have to check 500,000 names. Grover's algorithm, however, can find the name much faster. It uses quantum tricks to amplify the probability of finding the correct answer, cutting the search time dramatically. We also mentioned Shor's algorithm. While we didn't dive deep, it's important to know its name and what it does. Shor's algorithm is famous because it can find the prime factors of very large numbers incredibly quickly. This is a huge deal because most of the encryption that protects our data online relies on the difficulty of factoring large numbers. Bank transactions, private messages. Shor's algorithm threatens to break this encryption. It's a powerful demonstration of the disruptive potential of quantum computing. Great work this week. You're now familiar with the core principles and some of the most famous applications of quantum power. Welcome to our final week, Week 3. It's time to connect these amazing quantum concepts to the real world. First, let's talk about the hardware. How do we actually build a quantum computer? It's not easy. Qubits are incredibly fragile. Any little disturbance from the outside world, a tiny vibration, a stray magnetic field, a change in temperature, can destroy their delicate quantum state. This is called decoherence. To protect them, scientists often cool quantum chips to temperatures colder than deep space. There are several competing technologies for building qubits: superconducting circuits, trapped ions, photons, silicon quantum dots, and diamond NV centers. Superconducting circuits, tiny electrical circuits cooled to near absolute zero, used by companies like Google and IBM. Trapped ions, individual atoms held in electromagnetic traps and manipulated with lasers. Photons, particles of light used as qubits. Silicon quantum dots and diamond NV centers are also promising approaches. Each approach has strengths and weaknesses. The race is on to see which scales best. Even with the best hardware, errors are inevitable. That's why quantum error correction is one of the most important fields of research. In classical computers, you can just make copies of a bit. But the no-cloning theorem says you cannot create a perfect copy of an unknown quantum state. So scientists spread one logical qubit across many physical qubits using error-correcting codes. By measuring collective properties, errors can be identified and fixed without destroying the quantum information. Visual. One logical qubit protected by 9 physical qubits. This leads us to the current era, noisy intermediate-scale quantum, the NISQ era. Today's quantum computers have dozens or even hundreds of qubits, but they are noisy, prone to errors, and have short coherence times. They are not yet powerful enough to run Shor's algorithm on large numbers, but they're perfect for exploring hybrid quantum classical algorithms. A quantum computer does what it's best at, while a classical computer handles the rest. This teamwork gives useful results even from today's imperfect hardware. Small wins add up as hardware and algorithms improve. Now for the really fun part. It's one thing to talk about quantum computing, but it's another to actually do it. Thanks to incredible open-source tools, anyone with a computer and an internet connection can run experiments on a real quantum computer. One popular platform is IBM's Quantum Lab, which uses a framework called Qiskit. Qiskit is based on Python, so if you have experience with Python, you'll feel right at home. But even if you don't, the basics are easy to pick up. Let's imagine writing a simple program to create a state of superposition and measure it. The quantum hello world. You start by defining a quantum circuit with 1 qubit and 1 classical bit. The qubit is where the quantum action happens, and the classical bit stores the measurement result. With Qiskit, you can first run it on a simulator on your own computer. This is a great way to test your code and see the expected outcome. Because our qubit is in a perfect superposition, you should get a 0 about 50% of the time and a 1 about 50% of the time. Then, for the real magic, send your job to one of IBM's actual quantum computers in the cloud. After a short wait, you'll get the results from a real quantum device. Congratulations! You are now a quantum programmer. I highly encourage you to go try it yourself. We've done it. In just 3 weeks, we journeyed from bits and bytes to the frontiers of quantum mechanics. You've learned about superposition and entanglement. You've met Grover and Shor. You've seen the hardware and learned how to write your first quantum program. Take a moment to appreciate how much you've learned. This 21-day journey was just the first step. You have the map and the fundamental skills to climb higher. Play with Qiskit. Use IBM Quantum Lab. Build a Bell state. Experiment more. It becomes intuitive. Quantum computing can transform industries, design new drugs, create novel financial models, develop cryptography, and build more efficient AI. You're at the forefront of change, not a spectator, a potential participant. Now go out there and change the world. Thank you for joining this adventure. The quantum future is bright, built by curious, passionate people like you.